Okay, so today we're going to be looking at intrinsic silicon and how it works as a semiconductor. So you're going to hear the term intrinsic sometimes, or sometimes you'll hear pure, but these are interchangeable. They just mean a structure made out of pure silicon or just silicon. So silicon is a very good material because it behaves as a semiconductor. And to review what a semiconductor is, we're going to first look at insulators like glass and wood, and some conductors like copper, which is what a lot of wiring is made out of, and aluminum. We see that insulators aren't good at conducting electrons, whereas conductors are very good at conducting electrons and moving them through their structures. So semiconductors are going to lie somewhere in between here, semiconductors. And some semiconductors include, of course, silicon, and other semiconductors, germanium, that's used often in electronics. So a semiconductor behaves either as an insulator or a conductor, and that depends sort of on the atomic structure of the material or the temperature the material is at. So we will see that at lower temperatures, semiconductors will start behaving as insulators, and at higher temperatures, semiconductors start behaving as conductors. So we're going to specifically look at silicon and how this happens. So first, we have this silicon structure, this pure or intrinsic silicon. And some background information to know is that silicon has 4 valence electrons, right? So valence electrons are just electrons on the outermost shells of these atoms. These are electrons that are easily removed from the atom and could move around a structure. So in this structure, we're going to assume 0 degrees Kelvin or 273 degrees Celsius. So not necessarily 0 degrees Kelvin, that's impossible, very close to 0 degrees Kelvin. So at near 0, we'll see that these covalent bonds hold the silicon atoms in place and the electrons in place. So these electrons, like say this one right here, can't move out because it's inside of this covalent bond. So it's not free to move. So it's behaving as a insulator right now. But let's say we go to room temperature, which is about, it's 200. Oh, let me change colors. It is about 293 degrees Kelvin. Oh, it's just Kelvin, not degrees. So 293 Kelvin or 20 degrees Celsius. So what we'll see start happening at this temperature or room temperature is that these covalent bonds, they start to break, right? So this temperature, there's enough energy in the structure where this covalent bond breaks. And that means that this electron is now free to move around the structure. All right, so let's say it moves here for right now. And what we're left with is a positive 1 charge in this silicon right here, circled in red. And what we'll sometimes refer to that is a hole. We have a hole here, which is the absence of an electron. So now there's the ability for an electron to move to that place. And what we'll see is that this temperature, maybe this other covalent bond, starts to break as well. So now this electron is free to move around the structure and it's attracted to this hole. So this silicon atom no longer has a +1 charge, and we'll see that this electron on the right fills the hole that was left by the other electron. So we'll see that these covalent bonds form again. But what will happen is these covalents will break again somewhere else. So they'll break here, and they'll break here, and we'll see this process happen over and over again at this temperature. So there are two things occurring at the same time. There's the breakdown of covalent bonds, and there's also the recombination. Right? So from this idea, we could sort of create an inequality. It says that n, we'll let n equal the amount of free electrons, right, that aren't stuck by a covalent bond, amount of free electrons. And we'll let P equal the amount of holes. But really not the amount, we refer to it as the concentration. So concentration. Doesn't fit. Concentration. So N is the concentration of free electrons and P is the concentration of holes. And from here we could, since the breakdown and recombination of covalent bonds is happening sort of at the same rate, we could say that the concentration of electrons is equal to the concentration of holes. And from here we could also say that that's equal to Ni, where Ni refers to concentration, well, leave it at that, concentration of electrons and holes per a unit of volume in intrinsic silicon. And there's actually a formula that determines the concentration of electrons and holes per unit volume in intrinsic silicon. So that equation is Ni equals B times T to the R over 2 times E to the negative E G times 2K T. So we're going to go over these constants, but I need these variables, but I need some space. So P refers to a material dependent constant, and for intrinsic silicon, that is 7.3 times 10 to the 15 centimeters, so negative 3 Kelvin to negative 3.2. And then T refers to temperature in Kelvin. E is just Euler's number, right? That's a constant, 2.718, and so on. E to the G, so we called band gap energy. And band gap energy is just the minimum energy required to break down a covalent bond. And for intrinsic silicon, that's 1.12 electron volts. And lastly, we have K, which is Boltzmann's constant, which is just a constant. I'll just write that out. Boltzmann's constant, which has a value of 8.62 times 10 to the negative 5 electron volts Kelvin. So we're going to use this formula to sort of solve some problems. The first problem we're going to look at is calculate Ni for silicon, which is just Si for Si at 300 Kelvin. So Ni, if you remember, is just the concentration of moles and electrons per unit volume. And we're just going to rewrite our equation Ni equals Bt to the 3/2 times e to the negative Eg times 2kt. And we're going to solve this problem together because it's just a plug-in chug. So just plug in our values that were previously stated. Okay, so after plugging everything in and solving with either a calculator or by hand, if you like, we find that we have 1.5 times 10 to 10, and we call these carriers because they carry charge. Carriers per centimeter cube, right? So we have a carrier can either be a hole or an electron. Okay, so that was all I wanted to go over. It was mostly this idea of how temperature affects the silicon structure and how it's actually able to conduct electric current through its structure based off temperature. So that's it for today. Next, I want to talk about p-type and n-type silicon and how that's used in electronics.